Hello, mechanical transmissions class. Travis Bledsoe. I'm back with another video lecture for belt drives. Our last section was over bearings, and now we're doing belt drives. Next, we'll do gear drives after this one. So the next 3-4 slides are going to show applications of belts. So the pulley that the belt rides in is also called a sheave. So you may hear me refer to it as a sheave or a pulley. This shows a double belt application. It's one that probably has a high tension or a high load from the equipment being driven, and that one belt is probably not strong enough to maintain continuous application. So they can make a double, there's triple, there's as many belts as needed. They can make sheaves to accommodate more than one belt. Here's an application of motor driving a large blower fan. Here's also applications of motors driving blower fans, but these slides, I have these here really to show the guard application, how a guard needs to be across the belt at all times when it's in operation. So you would only take the guard off when the motor is locked out and tagged out. The one on the left has just a face cover to go over the guard. You can have access into the belt, check tension or replace the belt or sheave. So there's two types of power transmission belts. They're friction drive belts and positive drive belts. We'll talk more in depth about each type, but in general, the friction drive belts are going to be your flat belts that um, maintain a positive, a really tight um, connection between the sheave and the belt, and then your friction drive, another friction drive belt that we'll talk more in depth about in this video is the V-belt. So it operates on friction along the sides of the belt into the sheave. And then the positive drive belts, they're actually a belt that have teeth in the belt and in the pulley that the belt rides in. So there's less tension there than it is with friction drive belts. Friction drive belts, they're V-belts. They use the principle of a wedge, so the belt is angled as well as the sheave, and the angle, when you tighten it down, the belt grips inside of that sheave and creates the wedge friction between the sheave and the belt. They use less tension as opposed to a flat belt. The old flat belts you'd see in old applications like I know I went to the Wright Brothers museum. That's all they had when they were working in their bicycle shop and their airplanes. All their equipment was run by flat belts. On those belts, you have to get a really, really tight connection between the belt and the drum. Essentially, is what they run on. It's a little flat drum pulley. They were so tight that the bearing life would fail. We talked about bearings before and the loads, so you have to make the belt so tight that it really put excessive wear on the bearing. So the friction drive belts or the V-belts, when they come out, are saving the bearing life. So they're more popular than the flat belts today. Positive drive belts are the synchronous or timing belts. They're a belt with a sprocket and which have teeth on both the sprocket and the belt. So we'll get into V-belts. So there's advantages of using V-belts, and this is advantages as opposed to gear drives or chain drives. So they're relatively low cost and they're pretty quiet in operation unless there's a misalignment or a bad belt or something, or a heavy load. So no lubrication is required as opposed to gears and chain drives. There's a broad range of ratios and sizes. You can change the sheave size um, and change the speed of the application. Fairly easy. And they're relatively easy to install. So this is a slide that I'll repeat later into the slide deck here. This is showing different types of V-belts. You've got a classical V-belt that uses letters A, B, C, D, E. This is part of their sizing. And then there's a narrow groove belts that have a V in it. It's 3V, 5V, 8V. When the manufacturers make these, whether you get them, it doesn't matter which manufacturer makes the belt, there's industry standards with the V-belts. So you can see that, say, a C belt is going to be 7/8 inch wide at the top, and the height is going to be 17/32. So manufacturers are going to make these to these industry standards. So let's look at, I want to really quickly mention that the strength of a belt. Notice there's a lot of material here in the belt. There's an outer cover, which is really just to protect the inner part. So you have a lot of filler material. It's rubber. The strength of the belt is coming from these fiber cores that's along the top, and you'll see different configurations of these. These are little three-piece fiber cores put together along the top edge of the belt. And you can see the ones at the bottom that have the fiber core. That is the strength of the belt. So if you damage the belt or damage the fibers, then it's likely to will break. Your strength is not coming from the filler material, the rubber, or the outside cover. So down at the bottom of this slide, we're seeing where the one on the left shows a good application, a good fit for a V-belt down into a sheave. So this lighter gray part is the sheave, and the dark colored is the belt fitting in. So you have a large gap at the bottom, and you don't have much of the belt, if any, sticking out of the top. So that shows a really proper fit for your belt. So your friction is coming from this side, the side walls. That's where it's contacting and making the driver, the motor, and the driven sheave turn. You can see on this middle one that the sheave is starting to wire, and it's starting to get curved out a little bit. And then you're having a drop in the drop in the top between the edge of the sheave and the belt. It's still usable and will run like this, but it's nearing time to be replaced when you get down to a 1/16 of an inch drop into it. And the one on the right shows one that is absolutely worn out. So the sides of the sheave are concaved in. The belt is running on the bottom of the sheave, of the pulley. And this is an application that you do not want. So it's time to replace the belt and sheaves when you get to that. All right, now belt drives in this section, the hardest thing is going to be, as far as remembering for the test, is going to be the sizing. Each type of belt has a different sizing method. You would think that they'd try to standardize that, but they did not. So it doesn't make sense how the classical V-belt are sized and a narrow groove V-belts are sized. They're totally different. So keeping up with that is going to be the hardest part. I mean, other than that, V-belts and timing belts are fairly simple drive devices. So here we have the classical V-belt, and that was one in that one slide where it showed the cross sections and that had the A, B, C, D, and E. So that's going to be your 5 cross section sizes, A, B, C, D, or E. The classical V-belts you may hear referred to as conventional or standard V-belts. We're going to look at the sizing, the belt size, the letter followed by the a number. So, example, you've got a B, a cross section size of B, and then the number 90. So this is going to be the um, the 90 represents the inside circumference of that belt. So if you can measure the belt around the inside circumference, it's going to be 90 inches. And this is just representing the cross section sizes, which should align to the slide that we looked at earlier about the industry standard sizing of the belts. So your cross section size is going to be a letter, and then you're going to have a whole number after that. So the 90 represents whole numbers in inches on the inside circumference. There are no half sizes on these. When we get into the next belt we're going to talk about, we have half sizes. So the narrow groove V-belts, because the way they're designed and sized, they can handle more power and they use smaller diameter sheaves than the classical V-belts. So these are a little newer generation, although the classical V-belts are still used in a wide range of applications, industrial applications. So we only have 3 cross section sizes as opposed to the classical V-belts, where they had 5. But if you see the letter V in your 3V, 5V, 8V, if you see that, it automatically should tell you that it's a narrow grooved V-belt. If it has a V in it. So 3V, 5V, 8V, that's the 3 cross section sizes. So we have a belt that's labeled 3V 375. This 375, there's a hidden decimal place at the 10th, at the last number in your series there. There's a hidden decimal place. Trying to find the mouse again to show right there. So this belt size is going to be 37.5 inches. So your 3V is your cross section size, which is industry standard. We're not going to have that on the test, but I want to know what the length of the belt is on the test. So this is a 37.5 inch belt, and these are outside circumference, whereas the classical V belts were inside circumference. Like I said, how they come up with the sizing of these, you would think they would have a standard size, but there's not. So the classical belts have they come in whole inches. There's no half sizes. You get a narrow grooved V belts. There are half sizes. So this was a 37.5 inch belt. There's a hidden decimal place there. It's not printed on the belt or on the packaging. So you have a cogged V belt. Cogged V belts, they had the same sizing as your standard or classical V belts and your narrow groove V belts. All the difference is they have notches cut out on the underside of the belt. I'll show you pictures of that in coming slides. These notches help with better flexibility, so you can use a smaller sheave. The belt can actually bend a tighter radius, and they dissipate the heat because you got more open section because of that notch there. You've got more open section, and the heat will dissipate faster. So they're a good application. So the only difference in the sizing when you have a cogged V-belt, and it can be in the classical V-belt configuration or the narrow grooved V-belt configuration, you're going to have an X in the sizing designation. So our example for the classical V-belt was a B90 in the previous slide, B90. So it's a cogged configuration, it's going to have an X. So you'll have a BX90. And then in the narrow grooved sizing on our previous slide was a 3V375. So if it's the same belt, but it's has the cogged configuration, you're going to have an X there. So it'll be 3VX375. So remember, if you got an X in the designation, it's going to be a cogged V-belt. Banded V-belt. These are just multiple V-belts attached with a common backing. So as I mentioned earlier, you can have shiv setups where you can have more than one belt aligned. You can have 2, 3, 4, 5 belts running simultaneously in the shivs. This banded V-belt, it connects all those belts together with one common backing. So what this helps with is it makes sure all the belts are the same length, so they're sharing equal load. And then it eliminates belt turnover. So you have a really rough application for a belt. It has a lot of jerking and uh, pulsing load. So you can make your belts whip, make them flip and turn over and start running on their sides or upside down in some cases, or make the belts jump off. The banded V belts really help eliminate the belt turnover, the belt whip, and the belt jump off. Keeps all the belts together. Fractional horsepower belts, and these are kind of in line with the sizing of the narrow groove V belts. These all they are is a light duty belt. So if you see an L in the designation, you have 4 designations, cross section sizes. Excuse me. You have 2L, 3L, 5L, 4L, and 5L. So if you see an L in that, it's going to be a light duty fractional horsepower belt. So our sizing is going to be, for the example, is a 3L 335. There's a hidden decimal place there. So you're going to be 33.5 inches. So these sizing are like the narrow groove V-belts. They come in half sizes. Variable speed V-belts. These are wider than your conventional V-belts. You've actually used those in our lab on our drill presses. They have variable speed V-belts. So during our lab coming up in a couple of weeks, I'll take the cover off the one of the drill presses and show you how that operates. It's a really neat, simple principle. So they're wider than the normal V-belts. They handle high horsepower requirements, operates on shivs with movable sides. That's the key word there. Notice it's red. Operates variable speed V-belts operate on shivs with movable sides. One of the shivs is spring loaded and the other one is adjustable, either manual or electrical. But in our application and with our drill presses is a manual adjustment. So use the handle on the side to open or close the shiv inside, then the opposite shiv is going to be spring loaded to compensate. It'll make more sense when you look at it. So double angle V-belts is another type of friction drive belt. These actually have the V notches on the bottom and the top. And that way you can transmit power from both the top and the bottom half of the belt. So these can run in very odd configurations and still drive. So you can kind of do S loops and figure eights with these or whatever application that you need power driven from different angles of the belt, different sides of the belt. So these are going to be a special version of the classical V-belt. So we're going to use the classical V-belt sizing codes. And since it's a double angle, we're using the letter code and it's going to be doubled. So the classical V-belts, remember there were A, B, C, D, and E. These are going to be AA, BB, CC. So that's going to be an indicator that it's a double angle V-belt. So we're back to this slide again. So maybe this slide makes a little bit more sense now after you've seen some of the sizing of the V-belts in the previous slides. Really nothing more to add, just to show that you got classical V-belts along the top, your narrow grooved along the second line here, and then the sizing will be along the outside and inside circumference. So here we're looking at some cross-section views of V-belts. So you've got a classical V-belt on the left side, letter A, and it shows a cutaway. So you see the fiber cores inside along the top edge. That is the strength of the V-belt. So here's a picture of a cogged belt. I should put this picture on the slide itself. That way you can get a visual while we're talking about it. So the cogged belt is just notches cut inside. So they can actually make a tighter loop through a smaller sheave. And then since there's more surface area showing open to the air, it keeps the belt cooler. Again, there's really no less strength involved in these because your strength is coming from this core in the top. And then a cross-section size of your um, the double angle V-belt. So let's notice the sizes. So we start out with your classical V-belt, what's an A. Then we have the cogged V-belt, and it has an X in it, so AX. And then we have a double angle V-belt, it's a AA. So now this is a formula that you can use to calculate the length of the belt. So if you have an application that you just something you just set up, you don't have a belt for, or if the belt breaks and it's disintegrated, that has no markings on it at all, to try to cross-reference, excuse me, cross-reference the size, you can use this formula to calculate the belt. So all you need to know is your diameter of your smaller sheave and larger sheave, and then the center to center distance. The formula looks complicated, but it's really not. It's pretty easy, and we'll do this in lab. But to run through it right now, if you want to grab a calculator, uh, paper, and some pen, let's talk through this. So we've got the smaller sheave. Let's say it is 4 inches. And notice it's a lowercase d, so it's talking about the smaller sheave. And the uppercase D is talking about the larger sheave. So we have an 8-inch uppercase or 8-inch larger sheave. So 4 inches smaller, 8-inch for the larger. And we've got an application where the center to center distance is 36 inches. So you can measure either from the top of the sheave at the crown to the very top of that to get your center to center distance. But also in real life application, you're going to have a shaft sticking out the center of this. So you can measure the shaft as well, the center of the shaft of one to the other, which is going to give your center to center distance. Okay, so let's plug the numbers into the application here in the formula. So we got the C is representing your center distance. So it's 36 inches times 2, and it's going to be 72 inches. The way I usually do this is work from left to right and then come backwards. I mean, I'm not a math whiz, so unless you got a calculator that can do all this as you punch it in, I'll just use a simple calculator and I'll just write it down. 2C, write down 72 inches. You come to your next section. Always do what's in the brackets first. So you're going to add your smaller and your larger and your smaller sheaves. So we have an 8-inch sheave and a 4-inch sheave is going to be 12 inches. Then you're going to multiply that. Since brackets, you multiply that times 1.57. And that's going to give you 18.84 is what I got. And then you come over to this section, do what's in the brackets first. So we're going to subtract the smaller from the larger sheave. So it's 8 minus 4, and it's going to give you 4. You're going to square that, so you're going to have 16. And 4 squared is 16. It's 4 times 4. And then that's going to be over, be divided by 4C. And so you're going to multiply your center distance, C, by 4. And you're going to get 144. So this last section, you're going to have, I get the mouse back up where I can show you. So it's going to be 16 divided by 144. So the answer is going to be, and the next section is going to be 0.111 continuously. 0.111. So now work backwards and just add those together. So 0.111 plus 18.84 for this middle section plus 72 for this first section is going to come out to be 90.95, 90.9 inches. And you'd round that up to a 91-inch belt. So you're not going to find a 90.95 belt. So, but um, you have adjustments in your typically on your motor and your driver. Is what you would adjust. So you can adjust within a half an inch or an inch or so. So it'll be a 91-inch belt. So work through that. That'll be on the test. We can work through that in the lab as well. If you have any questions. So V-belt installation and tension. I'm sure if you've ever dealt with V-belts that you've tried the run-on method or you've seen people use the run-on method. That's really, it's an easy way to do it, but it stands the chance of ruining the belt. So like I mentioned, the fiber cores inside the belt are the strength. So if you stretch or damage those, you are decreasing the lifespan of that belt. So as the slide shows, never install the belts the pry bar method or run-on method. The ideal tension should be the lowest tension at which the belt will not slip under peak load conditions. So you don't need to tighten it down extremely tight, just tight enough to where the belt is not going to slip. And oftentimes when they slip, you know it because you'll hear a large, loud squealing sound. They make a V-belt tensioning device is shown here in the bottom. And we'll have to talk about that in lab because it's so small. And I'll try to put a link to a video underneath this video in the comment section if you can click on the link that maybe shows the application of that and you can get an idea before we get into the lab. So the proper belt tension, you're going to use a straight edge method, and that's what you'd use the belt tensioner guide in the bottom using the straight edge method. So you've got your larger sheave, smaller sheave. You lay your straight edge, which is represented by the dotted line, and then you press the force down onto the belt. This belt deflection ideally would be 1/64 of an inch belt deflection per inch of span. So your span length is going to be your center to center distance of your application. So your center to center distance between your larger and smaller sheave. If it's 36, like in our example in the previous slide, if you have a 36-inch center to center distance, it's going to be the easiest way for me to do it is just put 36 over 64, and that's going to be the proper belt deflection. So if you can round that down to the lowest fraction, which is going to be 9/16, 4 will go into 36, 9, and then 4 will go into 64 16 times. So it'll be 9/16 should be the gap between your straight edge, represented by the dotted line, and the as the belt is deflected down. So 9/16. I'll show you how to use these. There's no way to do that unless I can get a video to show you, and then we'll actually have it in hand. There's different markings on it, and you've got O-rings on the smaller plunger and on the larger body of that. So we'll look at that definitely in the lab, and hopefully I can give you a link to a video you can watch. So positive dry belts is our next section. As I mentioned, positive dry belts have notches in the belt and in the sheaves. They run in synchronous timing. So these are using timing belts in your cars or any other timing application in industrial use. You'll use a timing belt. These do not allow slippage. Any slippage occurs, and then there's going to be damage to the equipment. So looking at the synchronous belt, also called timing belt, you have teeth in it. So from like our threads that we talked about, the pitch of a thread, it's kind of similar with our synchronous belts. We have pitch for tooth to tooth. So the corresponding point on one tooth to the other tooth is the pitch. You'll see that in the sizing of the belts when we get into that slide. So that's the pitch. This slide, the positive drive belts, synchronous belts, most commonly called timing belts. Timing belts are made in 5 standard pitches, and those, remember, the pitches with the tooth-to-tooth sizing. So this is the pitch distance between one tooth to the next tooth: 1/5 of an inch, 3/8, 1/2, 7/8, and 1 1/5. So we have a code designation that's going to be stamped onto the belt or on the packaging. You're not going to see 1/5 or 3/8 listed. It's going to be listed as a code. This is a pitch code. So XL is representing this pitch 1/5. L is representing 3/8. H is representing 1/2 inch. XH, extra heavy, would be 7/8, and then XH would be 1 1/5. So you've got the extra light, light, heavy, extra heavy, and double extra heavy. So we have standard widths and manufacturer width of these. So you've got as small as a 1/4 inch on your 1/5 up to a 5-inch wide belt on your double extra heavy belt. And then the sizing of these, again, is another catcher of the belt sizing. As I mentioned, this is the hardest part of the belt course, is keeping up the sizing of the belt. So your belt code, your sizing is going to reflect the length, the pitch, and then the width of the belt. So here we have 900. That is your length. But there's a hidden decimal place at the 10th. So we've got 90 inches is your length. There's always a hidden decimal place right there. And you have H. This is going to be your pitch code. We're not really worried about that. That's a standard, industry standard size. Just know that that H is representing the pitch. And then your 300 is going to be your width. Again, there's a hidden decimal place, but this is at the 100th place. So these 2 zeros are to the right of the decimal place. So the width of the belt is going to be 3 inches. So if you get confused with this, whether the 900 is the width or the length, or the 300 is the width or the length, remember the decimal places at least. So you're going to have a decimal place of at the 10th for the 90. So a 90-inch belt, that's logical. A 90-inch wide belt, that's not logical. So for a 300, if you can remember the decimal place is at the 100th. A 3-inch long belt, that's not logical. Or a 3-inch wide belt, that makes sense. So if you can remember the placement as well as the length, pitch, and width, so you can look at if you forget where the decimal place is at on the width on the last section, if you put the decimal place at the 10th and you think it's a 30-inch wide belt, well, that don't sound right. So just remember that the decimal place goes at the 100th. You have the length, the pitch, and the width. So here's some links to videos that I'll try to get the videos into the or the links into the comment section below this video. So if you have any questions, feel free to email, and we'll catch up in lab on any questions that you may have. But it's rather straightforward on belts. They're not very complicated except for the sizes. That's the hardest part. So I will see you in the lab.